Lesson 3 of Chapter 7 is on hyperbolas. So we've already gone over some of the cross-sections of a cone. We've gone over a circle, an ellipse in Lesson 7.2. We went over a parabola in Lesson 7.1. So that leaves us with a hyperbola. And if you read the paragraph at the top, it says conic sections, or conics, are figures formed when a plane intersects a double-naped right cone. It's kind of a mouthful right there. What the heck is a double-naped right cone? Well, you can see each of these pictures has a cone on the top and the bottom. That's the upper and the lower nape. And when we went over the cross-sections of circles and ellipses, you're just going through the lower nape. Same thing with a parabola. You can see that the picture shows that we're just going through the lower nape, or the bottom cone, right? Well, with a hyperbola, your cross-section is going to intersect you through the upper nape and the lower nape. And so that's going to form what we call a hyperbola. Here are the parts of a hyperbola. We have a center. That's going to be a point that's right in between the two curves. Now this hyperbola is opening up and down. The orientation is vertical. But sometimes the orientation is going to be horizontal, left and right. We still have 2 points called vertices right here, kind of like with parabolas. And then we also still have 2 points called focus points. These points right there, those are inside the curves, right? And then that leads us to having 2 axes. One of the axes is called the transverse axis. That axis goes through all those points, the focus points, the vertices, the center, all right? The other axis is called the conjugate axis, and that axis is perpendicular to the transverse axis, and it passes through the center. So here's a picture. The picture on the left shows you a hyperbola that's opening up and down. That's the orientation. And the picture on the right shows a hyperbola that's opening left and right. But notice on both of these hyperbolas, there's a rectangle drawn. Well, that's going to lead me to the A, the B, and the C value. So let me talk a little bit about the A, the B, and the C value. But let's first look at this information. This shows you the standard form equations of a hyperbola. So here's one standard form equation. This is when the orientation is horizontal. Okay, you can see we got 2 fractions being subtracted and it equals 1. Notice that the denominators of those 2 fractions, it says a squared and b squared. Well, you know, in the last lesson with ellipses, we had an a, b, and a c value. The a value was always the largest with ellipses. Well, that's not going to be the case with hyperbolas. Okay? On hyperbolas, sometimes a is going to be larger than b, and sometimes b will be larger than a. Keep that in mind. We also have a standard form equation right here, and that's when the orientation is vertical. You can see that one opens up and down. Again, you've got 2 fractions being subtracted, and it equals 1 on the right. Well, that equation also has an a squared and a b squared in the denominator. Again, you're going to notice that sometimes a is larger than b, and sometimes b is larger than a. This is different than the way it was with ellipses. Okay? So we always put the positive fraction first. We put the negative fraction second. And you'll notice that both of these standard form equations have the a squared at the bottom of the first fraction. The b squared is at the bottom of the second fraction. But you'll notice on both those standard form equations, the h value is grouped with the x, the k value is grouped with the y. So the h and the k is going to tell you the center of the hyperbola. And then you can jot down this information on your note card. This information is going to tell you how to find the different parts of the hyperbola. Well, you'll notice at the very bottom, we have something. I've got the line crossed out where it says ABC relationship, and I put Pythagorean theorem because it actually is the Pythagorean theorem. A squared plus b squared equals c squared. So what that tells us is that with these hyperbolas, the longest value is going to be the c value. This is different than it was with ellipses in lesson 7.2. With ellipses, the a value is always larger than b and c. But with hyperbolas, c is always larger than both a and b. Well, let's go back to this picture that I have right here, and you can see that your a value is going to be the distance from the center to the vertex. Right here is your a value. Okay? Your b value is going to be the distance from the center to the edge of this rectangle right here. There's your b value. And then your C value is going to be the distance from the center to the focus point. That's going to be your C value. And you can see that right here. Okay. Same thing on the other one, except for the orientation is horizontal. So again, you can see that the A value is from the center to the vertex right here. The B value is from the center to the edge of that rectangle right here. And then the C value is the distance from the center to the focus point right there. In case you're wondering how to derive the standard form equation of a hyperbola, there's a standard form equation right there. You can go through this little proof here that shows you how it's derived. So let's do some graphing. Example 1 says to graph the hyperbola. So the first thing we're going to do is going to determine the center. And hopefully you can tell that the center is at 0, 0. Because there's no h and k value grouped with your x and your y, so that makes it pretty easy to identify the center to be 0, 0. Next, let's identify the a, the b, and the c value. The a is always the square root of the first denominator, so that's going to be a 3 because the square root of 9 is 3. The b value is going to be the square root of the second denominator, which is going to be a 5. And now to find the c value, you have to use the Pythagorean theorem. So 9 plus 25 is 34. Square root of 34 would be your c value. So here's how we draw a hyperbola. We start off by drawing the center at 0, 0. Now, we have to determine the orientation. And since y is being squared, as in the first fraction, above the a squared, you can see it's like the standard form equation on the right. So that's going to be vertical orientation. So since this is vertical orientation, we're going to take the a value and we're going to go up 3 and down 3 from that center. I'm going to plot a couple of green points right there. Then we're going to use the b value and go to the right 5 and to the left 5 from the center. This allows me to draw a rectangle like you saw in those pictures I had a minute ago. And after I draw this rectangle, that allows me to draw the diagonals. Now the diagonals represent the asymptotes for this hyperbola. Okay, those are asymptotes. The curve's going to get closer to those as you go further to the right and further to the left. Now we have to determine that this is going to be vertical orientation. So our vertex point was right here on that green rectangle, and then it's going to open up, approaching those asymptotes, and also open down, approaching those asymptotes, kind of like that. The focus points, square root of 34 is approximately a little bit less than 6. Let's call it 5.8. So if I go up 5.8, puts me about right there. That would be my focus point. And if I go down 5.8, that would put me about right there. That'd be another focus point. And then, of course, we got our 2 vertex points right there. So we've just graphed that first hyperbola that has vertical orientation with a center at 0, 0. Second example, you can see we're graphing this hyperbola, and this hyperbola has a center at -1, -2. That's your h and your k. Next thing we'll determine is the a, the b, and the c value. And so our a value is the square root of 9, which is 3. B value is the square root of 16, which is 4. And the c value is found by using the Pythagorean theorem. 9 plus 16 is 25, and the square root of 25 is 5. All right, let's plot that center at -1, -2. Now the orientation on this hyperbola is going to be horizontal because the x squared is above the a squared. So we're going to have to take the a value and go to the right 3 and to the left 3 from the center. Okay, then we'll have to go up and down 4 from the center. And that allows me to draw this rectangle. And once I draw that rectangle, that allows me to draw in the asymptotes for the hyperbola. So there's your asymptotes. And then we already said that this is horizontal. And so this is my vertex point, and the curve is going to open to the right, like this, and to the left, like that. So there's your 2 vertex points, and then your focus points would be found by going to the right 5 and to the left 5. So there's your 2 focus points. And that's the graph of this hyperbola that has a center at -1, -2 with horizontal orientation. Well, the last example I want to go over is right here. And this says to graph the hyperbola. What's different here is, of course, that it's not in standard form. So we have to put it in standard form. And we've been doing this with the last couple of lessons. I'm going to group my x values together. I really don't have to group my y values because there's only one y value together. Now let me factor a 2 out of the x terms. And I'm going to leave a little space that I can complete the square with the x's. And now, if I complete the square, I take the b value, -6, divide it by 2 and square it, and that gives me +9. I've just completed the square for the x's. But I do need to balance my equation, and since it looks like I've added 9 to the left, but really I've added 18 because there's a 2 in front of the parentheses. So I'm going to balance my equation by adding 18 to the right. And now I can rewrite this in a standard form with an x minus 3 to the 2nd power. And we get a 54 over there by adding 36 and 18. And one more step to get it in standard form, that's just divide everything by 54, because we got to have fractions equaling 1. So if I divide everything by 54, I'm going to get y squared over 18, because 3 over 54 is the same thing as 1 over 18. We're going to have x minus 3 to the 2nd power over 27, because 2 over 54 reduces into 1 over 27. So there's your standard form equation. And now hopefully you can tell that the center is at 3, 0. The a value would be the square root of 27, a little bit bigger than 5. The b value would be the square root of 18, a little bit bigger than 4. And the c value would be 27 plus 18, which gives us 45. And so the square root of 45, a little bit less than 7, is our c value. So let's plot that center at 3, 0. Let's see, the orientation on this is going to be horizontal because the x squared is above the a squared. So let's go to the right, square root of 27, which is, let's just call that 5.2. And to the left, 5.2. Let's go up and down, square root of 18. Let's call that 4.2. And down 4.2. And then we can take those 4 points, we can draw a rectangle. And then once we establish that rectangle, we can draw in the diagonals, which represent the asymptotes for this hyperbola. And then we've already discussed how this is going to open left and right. And here's my vertex point. Here's another vertex point. And this is going to open to the left, staying in between those asymptotes, and then also to the right. Focus point, let's see here, square root of 45 is a little bit less than 7. So, say about right there would be a focus point, and about right there would be another focus point. So that's a picture of this hyperbola after we've changed it into standard form, and it has a center at 3, 0.